In section 3.4, we're going to talk about something called the rational zero theorem. The rational zero theorem is to try to help us figure out other ways of solving for the zeros or the roots of a function, a polynomial function specifically. So it lays out here the full thing. It says we have this polynomial laid out with all the coefficients and terms, and it has only integer coefficients. So that's kind of specific here. It doesn't work for all polynomial functions, just those that have integer coefficients. If that's the case, and what we call p over q is a so-called rational root expressed in the lowest terms of the polynomial function, then p is a factor of the constant term, a0, and q is a factor of the leading coefficient, an. A lot to unpack here, but it's actually not too much once you get into it. It basically tells us what we could see for possible zeros of our function. Specifically, possible rational, they call it zeros. Rational because they're written like a fraction, p over q. So possible rational zeros can include this p over q, where the top number p is going to be a list of all the factors of the constant term at the very end. And that, again, that one comes last at the very end. And q is going to stand for all the factors of the leading coefficient, which I'll just abbreviate here LC. Leading coefficient is out in the first position. So a lot of times I like to mention to people to think of P as past, so it comes in last. Q can be thought of, I guess, as quick, so it comes in first. And this is just to help remember what that P and Q is referring to when we talk about these possible zeros. P for past, it comes in last. Q for quick, it comes in first. So here's a polynomial, and I'm not going to solve it. I'm just going to list out some possible zeros for the polynomial function. So by the rational zero theorem, we do this by the, again, p and q numbers, where q stands for, you can think of quick, it comes in first. So that would be the leading coefficient of 1 in this case. And p is past, it come in last at the -8. So when we do the possible rational zeros, we think of the p referring to the -8 on top and the q referring to the 1 underneath. And I list out the factors of each of these numbers. So for 8, -8 or 8, either way, factors of 8 are 1, 2, 4, and 8. For the rational zero theorem, we think of it both for the positive number and the negative number. So both plus or minus 1 is a factor, plus or minus 2 is a factor, plus or minus 4, and plus or minus 8. So that now lists out the factors, plus or minus factors of 8. And for 1, well, there's only two numbers, plus or minus 1. So what we have to do is break this down into 1 over 1. We have to list out each number on top divided by the 1 underneath. So 2 over 1 plus minus 4 over plus minus 1 plus minus 8 over plus minus 1. And then we just list out, well, 1 divided by 1 is 1, then 2, 4, and 8, all plus or minus. These are what we call the possible rational zeros, or our possible zeros for our function. Later on, we'll go through and see if we can check to see if we can find one that actually is a zero. But for right now, this is just listing it out by the rational zero theorem. So let's look at this polynomial and also do the same thing to list out the possible zeros. So we have Q in the front and P is the last. So when I list out here the 6 and the Q for 3, and list out again the factors of each of these numbers. Factors of 6 plus or minus of each, there's 1, 2, 3, and 6. Factors of 3 are plus or minus 1 or plus or minus 3. Now I have to list out all the numbers individually, and so what I do is I go 1 divided by 1, 2 divided by 1, 3 divided by 1, and 4 divided by 1. But that's just with the 1 underneath. We also can list out 3 underneath, like 1 over 3, 2 over 3, 3 over 3, and 6 over 3. So we have to go through each of these numbers, put them underneath with the other numbers on top. So I'll simplify this down. We have 1 over 1. We have plus or minus 1, 2, 3, 4. We have 1 over 3, plus or minus 2 over 3. Plus or minus 3 over 3 is 1. Plus or minus 6 over 3 is 2. So notice how the 2 and the 1, they showed up another time. They've shown up twice, so we don't actually have to include them twice if we don't want to. It doesn't harm anything to put them down twice, but we don't necessarily have to there. So all these numbers, plus or minus, are considered the possible zeros for our function. So for this one, it says list all the possible rational zeros or roots. Use synthetic division to test and find an actual zero root. Use this to find the rest of the 0/roots. Okay, this is where we're going to start using the possible zeros with the rational zero theorem and choose some until we find one that works. So we're going to start with this equation, x to the third minus 5x squared plus 17x minus 13 equal to 0. We're trying to find the 0/roots here. We're going to use the p over q to start out. P is the negative 13, and q stands for the leading coefficient of 1. So we'll list out the possible zeros. Factors of 13 are just plus or minus 1 plus or minus 13 over plus or minus 1. So this looks like negative 1. So this looks like plus minus 1 over 1, 13 over 1, and that's it. Or let's list them out individually. Negative 1, positive 1, negative 13, positive 13. Those are 4 possibilities for solutions. They don't necessarily all have to be solutions. In fact, it's possible that none of them are in some cases, but we'll choose one and see if it works. So let's try the first number. Let's try x equals negative 1. And we're going to do this by synthetic division, like we did in the last section at the very end when we were solving with synthetic division. So we're going to use the negative 1 here. We're going to be dividing into the 1, negative 5, 17, and negative 13 from our equation. Now what I would suggest doing here is trying the synthetic division on your own and see what number you get for the remainder. And I'll work it through in just a second. Going through synthetic division, we'll get negative 1 minus, plus negative 5, so negative 6. Then we'll get a positive 6 plus 17 is 23. Then we multiply, we get a negative 23 and add, but that last number is negative 36. So our remainder is not 0. So that tells me that x equals negative 1 is not a root of our equation. So this is not a solution here. We'll try another number. So we can cross out the negative 1. It didn't work. But let's try the positive 1. Okay, and so you may want to try that using synthetic division and see if you get anything that looks better. When I use 1, just like before with synthetic division, it goes, starts off with a 1, then we get 1, and then add together a -4, multiply -4, add positive 13, multiply by 1, another positive 13, and add, and it turns into 0. So we do get what we want to have here for a solution. This tells us that x equals 1 is a 0 or root that we're looking for. So now we determined one solution. What we do from here is we take what's left over in our quotient, set that equal to 0, and continue to solve. So we have an x squared minus 4x plus 13 equal to 0. The reason why I'm doing this versus going back and trying more of the other numbers that we didn't try is now we've broken this down to just a quadratic equation. And we can actually use just a factor the quadratic or use the quadratic formula in order to solve it. So we have to think, can we solve this by either factoring or the quadratic formula? So when I looked at factoring this, it didn't actually factor, doesn't factor. So our only option to continue to solve is the quadratic formula. So we have our A is 1, B is -4, and C is 13. When I set this up into the quadratic formula, it goes -4 plus or minus the square root of -4 squared minus 4 times 1 times 13, all over 2 times 1. Calculating this out, we'll turn to plus 4 and then plus or minus square root 16 minus 52, all over 2. Now we're looking into the square root and thinking, okay, we're getting a negative number. Because when 16 minus 52, you get 36, -36. And that's still all over 2. So now we have the square root of a negative number. I'll put an I out in front and change that to a positive 36. So the positive 36, the square root of that is just 6. So we have 4 plus or minus 6i all over 2. And another cool thing is everything here divides by 2. 4 divides by 2 to 2, plus or minus, and 6 divides by 2, you get 3. So plus or minus 3i. So those are more solutions, but now imaginary solutions. So at the end, we can say that our roots / zeros, we had 1, we figured that one out from the synthetic division, and then 2 minus 3i and 2 plus 3i. Make up all 3 roots of this equation. Now let's look at one more here where we have to find the zeros of this function. And we're going to start out with using the possible rational zeros with the rational zero theorem. If you'd like to practice that, you may want to pause the video here and do the P over Q and see what you find for the possible zeros. In this case, the P is going to refer to the -8 and the Q, the 1 out in front. So we list out the factors of P over Q. For 8, it's plus or minus 1, 2, 4, and 8, all over plus or minus 1. So we're looking at plus minus 1, 2, 4, and 8. Or I guess we could also list it out as -1, +1, -2, +2, -4, +4, -8, +8. So hopefully of these numbers, hopefully one of them is a solution. But we don't know until we start checking which one is which. So let's choose one. let's try x equal to minus 1. And again, we use synthetic division to test to see if we get a solution. We're using our function, which has 1, -3, -20, -24, and -8. If I run through the synthetic division here, we'll start with a 1, then -1, -4, +4, -16, +16, -8, +8, and then finally added at the end, we do get a 0. So this checks out. Since we got a 0 for the remainder, x equals -1 is indeed a 0. However, the thing that we have left over from the synthetic division is what we're going to continue to use in order to solve. So this goes x cubed minus 4x squared minus 16x minus 8. We have that equal to 0, and we're going to continue to solve. Because we still have an equation that has x to the third, we're not quite to the point where we could use like quadratic factoring or quadratic formula in order to solve and continue to test another of our possible zeros until we at least get it down to a quadratic. In that case, then we could finally use something else to solve. So let's try another number. I'm going to try x equals -2. Now we're going to use the stuff from up above, using the x cubed minus 4x squared minus 16x minus 8 is what we're going to be using now. So running through the synthetic division with -2, always start with 1, then -2, -6, +12, -4, then -2 times -4 is +8, and that's awesome because we get a remainder of 0. Another number that checks out. So x equals -2 is another 0 of our function. Also, we now are left with something even smaller to continue to solve with, an x squared minus 6x minus 4. Now we're back to another quadratic equation. So do we want to try to factor, or would the only option be to do the quadratic formula? In this case, unfortunately, we have another one that does not factor. So we are going to have to use quadratic formula here, with a equal to 1, b equal to -6, and c equal to -4. So when I set up the quadratic formula using those numbers, it looks like -6 plus or minus the square root of -6 squared minus 4 times a times c all over 2a. This will calculate and we'll get +6 plus or minus the square root of 36, 16 all over 2. And so we'll get 6 plus or minus the square root 36 plus 16 would be +52 all over 2. So we've pretty well solved. The only thing that I'm doing now is just simplifying. Let's simplify that square root 52, for instance. To do that, I'm going to break down the 52 into its prime factors, 2, 26, and 2 and 13. So I can circle a group of 2's and bring that out to the front of the square root, leaving us with 2 square roots of 13. So this will now simplify down to 6 plus or minus 2 square root 13 all over 2. And 2 will divide through all the numbers on top to get 3 plus or minus the square root of 13. So in the end, we solved and we got 4 different solutions, a -2 and a -1 checked out through synthetic division. And then through the quadratic formula, we got 3 minus square root 13 and 3 plus square root 13. So this last one I throw in here just not really as a problem that we have to solve, but just something that might pop up in the description of some of the questions. It's about Descartes' rule of signs. If you see this at any point in our homework, you can just pretty much ignore it. But in case you get into one of the explanations in the textbook and you get a little confused by it, this is what it's referring to. Then it's a way of figuring out how many positive zeros or negative real zeros there are for a function. And just to summarize it real quick, for positive real zeros, it's the same as the number of sign changes or less the number of sign changes by a positive even integer. And that's pretty much the same thing for the negative real zeros, except they use a negative x here instead. So you could put a negative x there and run through sign changes to find a number for the total negative real zeros that it could have. We basically, for this one here, if we wanted to think about Descartes' rule of signs, we look at the number of sign changes we see here, from plus to minus or minus to plus. There's 1, 2, 3 sign changes. So the number of positive real zeros by Descartes' rule of signs could be one of two cases. One, it could be a total of 3, since there's 3 sign changes. Or it says it could be less by a positive even integer. So it could be this, or it could be a total of 3 minus 2 equal to 1. Descartes' rule of signs would tell us one of these two would happen for positive real zeros. It could be 3 or 3 minus an even number, like 2, which would be 1. When we look back at the function we dealt with, we actually did fine. On this one we solved it, and we actually only had one real zero. The others were imaginary. So Descartes' rule of signs would be true in this case. It's just not definitive because it often refers to one of two different cases that could occur.